Right, so this is lesson 3.7, composition of functions, video number 1. We're going to start with the drill from this day where we're proving whether functions are even, odd, or neither. For number 1, when we have to prove, we have to decide, do we think it's even, odd, or neither? Usually start with the one you think it might be. I know that normally absolute value would be even. So I'm going to try the even test first. And my even test says that f of x should equal f at negative x. So the first part of the test is easy. I just simply copy down the function. And then for the other side of the test, I need to substitute a negative x wherever I see an x. And when I do that, this negative x, whatever it would be, would just come out being x. Like if this was negative 7, it would be the same as finding the absolute value of 7. If this was negative 100.2, it's the same as finding the absolute value of 100.2. So the absolute value of a negative is the same as the absolute value of the same number, positive, plus 3. And because these are the same, I have just proven that this function is indeed even. All right, number 2, y equals 1 over x. I think to myself, oh, that's just a parent function, and the graph of that looks like this, which is rotation symmetric around the origin, which is odd, so I know to start with the odd test. Up here on absolute value, I knew a V-shaped graph reflects over the y, which is why I knew that one would potentially be even. This one odd, let's try. The odd test is f at negative x is equal to negative of f of x. So I need to start with the left side. F at negative x would be 1 over negative x, which is simply negative 1 over x. That negative sign, I guess I could, just in case there's any confusion here, say that that's 1 over negative x, which is the same as negative 1 over x. Maybe that's a better way to write it. And then for negative f of x, that means put a negative in front of the whole function, which simply gives me a negative 1 over x. These are the same, so this is indeed odd. All right, for number 3, a quadratic is typically, this quadratic here, x squared plus 4, is a U-shaped graph, which would be reflection symmetric over the y-axis, which is even. So I'm going to start with the even test, which is f at negative, just f at x equals f at negative x. All right, let's see if that works. F at x is x squared plus 4, and then f at negative x, I'm going to substitute a negative x and square it and add 4. Well, when you square a negative, it just becomes positive. And these are the same, so I know that it's even. Notice, it helps if you have an idea of what they're going to be before you start. I know that absolute value is typically V-shaped. Sometimes that V is moved around, and I know quadratic is U-shaped. And remember, if it's reflection symmetric over the y, it's even. If it's rotation symmetric around the origin, it's odd. All right, so today we're going to be looking at composition of functions, where we're putting one function into another function. And so, oh, that's supposed to say evaluate. Sorry, that's a T there. Just notice that. So for this first example, they tell me what f of x is and what g of x is. And then it says f composed of g. That's what that little circle means. It means f composed with g at -2. Now, when you were in geometry and you learned how to do translations, you were always told to work right to left. So we're going to do the same thing here. First, we're going to start by putting the -2 into the g function, and then we're going to take that answer and put it into the f function. Right? So another way to write this that you might be more familiar with is f at g of -2. And of course, we always work from the inside of the parentheses out. So I'm going to start by calculating g at -2, which would be -2 minus 7, or -9. So again, first I put the -2 into the g. Notice I wrote it in parenthesis notation, and I put the -2 into the g. Now I'm going to take that answer and put it into the f. So now I'm going to find f at -9, which is 2 times -9 squared, plus 3 times -9. It's going to give me 2 times 81 minus 27. And when I do that, I get 162 minus 27, which yields 135 as my final answer. All right, let's look at f composed. I actually meant for this to say g. Sorry, I'll make a correction on that. G composed with f at -2. This was supposed to be the reverse. I'm sorry about that. And so that means I'm going to take g at f of -2. So I'm putting the -2 into the f function first. So f at -2 is 2 times -2 squared plus 3 times -2. So I get 2 times 4, and that is a positive 4 when you square a negative, and this becomes -6. So I'm left with 8 minus 6, which is 2. Now I'm going to take that answer for my f at -2 and I'm going to put it into the g function. So now I'm calculating g at 2, which is 2 minus 7, or -5. Okay. Now notice, when we put we put the -2 into the g first and then the f, we got 135. When we put the -2 into the f first and then the g, we got -5. We did not get the same answer. Let's look at example 2. Example 2 asks us to derive a formula for f at g of x, or we could think of this as f at g of x. They're saying a formula because we're not substituting numbers in at this point. So we are going to take the g function and we're going to put it into the f function. In other words, I'm going to take this x minus 7 and put it into the f function, there and there. Let's see what I get. So I've got f at g of x equals 2, don't write x, write x minus 7 squared, plus 3, don't write x, write x minus 7. Alright, so I'm going to start simplifying this. This is 2 times x minus 7 times x minus 7 plus, I can go ahead and distribute that, 3x minus 21. Now, when I have two binomials, I'm going to go ahead and FOIL these. Remember, first, outers, inners, and last. So I get 2. The first term yields x squared. The outers and the inners can usually be combined. Negative 7x and negative 7x is negative 14x. Negative 7 times negative 7 is plus 49. Plus 3x minus 21. Okay, I'm going to keep going here. Now I'm going to be ready to distribute that to 2x squared minus 28x plus 98 plus 3x minus 21. I can get this 3x and the negative 28x together, and that gives me negative 25x. And the 98 minus the 21 is going to leave me with 77. Right. Now we're going to derive the formula where we put f into g. So we're doing g at f of x this time. So I'm going to have g at f of x equals, so now instead of putting the x minus 7 in, I am going to, let's erase this, I'm going to put f, this whole thing, right there. So instead of writing x, I'm going to write 2x squared plus 3x and then minus 7, and I'm done. There's nothing else to do. That's it. No simplifying. All right. Our next step, we are asked to verify that f composed with g and g composed with f are not equal to one another. Now we can see that they're different equations, but what we want to do is we want to look at them on a graph. So we're going to go to our graphing calculator. So I've gone to y equals, and I've typed each equation into y equals, and I'm going to hit graph, and sure enough, they are not the same. So I could draw a little sketch of this on my paper. All right, so all I did here was I just drew a little sketch of what I had seen on the graphing calculator. All right, so moving on to example 3. I'm going to continue doing what I did before, f composed with g of x, so that's f composed with g of x, so I'm putting g into the f function, so I'm going to put square root of x right here, so f at g of x is equal to the square root of x squared. Well, when I square a square root, I simply just get x. Because remember, this is the square root of x times the square root of x, which would be the square root of x squared, which is simply x. I just think of the fact that when you square a square root sign, it gets rid of the square root sign. So my formula for f of g of x is simply x. Now we're asked to derive a simplified formula for g of f of x. So g of f of x. So this time we're going to take this function and put it into here. So that's the square root of x squared, which is x. Well, look at that. We got the same thing. When this happens, when f at g of x and g at f of x are the same, that means they're inverses. So if f of g of x equals g at f of x, and they both equal x, not only do they have to equal each other, but they have to equal x, then f and g are inverses.